We're working through the last two solutions to the word ratio practice questions in this video. I'm actually going to start with 5 though, because it's much easier than number 4. So here we're after the specific heat capacity formula, where M is the mass of the water or alcohol, C is the specific heat capacity, and delta T is the change in temperature. And none of those things are constant, so we're going to need them all. So for the water, we've got a mass of 80 grams, that's its specific heat capacity, and we're heating it up by 40 degrees. And for the alcohol, a very small mass there, that's its specific heat capacity, and again, heating it up by 40 degrees. So now we're ready to write the ratio. As we said, no constant, so there's nothing to cancel, but we can go straight ahead and put our values in. And this gives 2.7 times 10 to the 3 for that one. Right, question 4. First of all here we have to work out a fairly horrible gas laws question. Now we're after density, and density is mass per unit volume. When you're at sea level, we're told the density is 1.3 kilograms per meter cubed. So what we're going to do is we're going to say that we know at sea level 1.3 kilograms, we know that the volume of that is 1 meter cubed. And so we're going to ask at the top, what's the volume? And then once we know that, we'll be able to calculate the density. Now, if you look at the other information that we're given, we have got that the pressure at the top of the climb is 0.35 times the pressure at sea level. And then converting to Kelvin there, we've got the temperature at the top, 240 Kelvin, and the temperature at sea level, 293. And it's air we're talking about, and we're trying to find V, we've got pressure, we've got T, so the formula that we're going to use is the gas laws formula. We know P, we know V is what we're looking for, we know R is a constant, we know T. What about N? How many moles of air are we talking about? Well, if we've got 1.3 kilograms at the bottom and 1.3 kilograms at the top, we've got the same number of moles. We don't know how many moles it is, but we know that it's the same top and bottom. Now it's up to you how you want to do this one. The way I normally do it is to get everything that's changing on one side and everything that's constant on the other. So here we've got P is changing from sea level to the top, so is V, so is T, but the number of moles isn't, and obviously the gas constant isn't. So here's everything that's changing on one side, everything that's not changing on the other. Now what that means is that if I do sea level and top of the climb, then that means PV over T at sea level has to equal PV over T at the top, because they're both equal to this same number here. Now I'm going to put these values in. I'm just going to put V for volume at the top, the thing we're looking for. Now I can cancel P from there, and so if I work that out, I find that my 1.3 kilograms of air has expanded to fill 2.34 cubic meters by the time it gets to the top of the mountain. Now I can go back to my density formula and simply calculate what the density of air will be. Sorry, I'm substituting already there, V. And so we get finally a density of 0.56 kilograms per meter cubed at the top of the mountain. And now finally we're at our last word ratio question, and we're talking about Somerville's lungs at the top of the climb and at sea level. We want the number of air molecules, that's capital N. So if I knew the number of moles at the top and bottom, that would be really easy, but I don't. So we are going to have to use the gas laws formula again, but this time we're going to use the one with Boltzmann's constant in. So we're going to be needing the pressure of the air in his lungs, the volume of his lungs, and the temperature of air in his lungs. Now, of course, we already had the pressure and the temperature, so copying from the previous part of the question, we've got pressure at the top, 0.35 times pressure at the bottom, temperature at the bottom, 293, at the top, 240. And then we're told, assume that the volume is the same. This is the volume of his lungs, remember, so the air that we're looking at. And then there'll be less air molecules in his lungs at the top, because we know the pressure's going down. Okay, so we're ready to write the ratio now. And as usual, the first thing I'm going to do is sort out dividing by a fraction. And then we can cancel just the k's there. And here we are. We can now put our values in. So I'm just make sure I get them the right way around. So the top is this set here. So we've got 0.35p times v all over 240 times the sea level lot. So that's 293 over P times V. There we go. Cancelling again, cancelling the P's, cancelling the V's. That leaves us with and that finally comes out as 0.43. That's our final ratio there.